So, welcome to the Introduction to Numerical Computing. This is actually a submodule of a workshop that I'm also holding for the master degree. And in this case, we're going to cope with why numerical approximations are relevant in the field of game developing. And so, just to provide a short intuition of why that is relevant, you've also already seen that in order to simulate the application of a force, then the thing that you will need to do is to do an integration of acceleration from the force, given that you know the mass of the object and the force being applied to that, then you are able to determine which is the acceleration. Then given the acceleration, you're able to determine the velocity, and then given the velocity, you're able to determine which is the position given the delta time that is required for a simulation of a physical phenomenon. You may end up with scenarios where different algorithms for simulating time in a physical simulation will have different precision outcomes, and the reason for that is actually how the numerical operations are performed. So for example, in this module we are just seeing the naive Euler method to do integration, but there are also more sophisticated methods like, for example, Runge-Kutta, that actually provide more precise outcomes that are also less efficient to compute. So they're not the best choice for video games, but are best choice if you want to do actually an accurate physical simulation of a phenomenon. Well, on the other hand, there are also other trial and error approaches that are going to provide more accurate results that are not going to be discussed in here. So, another problem that you have inside video games, and that is also very prone to numerical error, is also the collision detection. Why is that? So you may want to consider that you have a very big field, and inside this field you have some warriors that are trying actually to hit themselves, or even they're hitting the sword. So if you compare the size of the field, which is actually a bunch of a lot of kilometers, and you try to compare that with the size of the swords that are just 1 meter or less, then you will have really a problem if you have a very big battlefield to detect all the possible collisions. Because actually you will have that even the swords are trying to collide, then given that they are very small, they could be seen by, after doing some numerical approximation, as nearly parallel. So you also have a problem in doing accurate collision detection in there. So we're just trying to provide in here a naive technique, which is actually using interval arithmetics, while, for example, more advanced and sophisticated ways to do collision detection for OBBs that are not also considering at the moment are going also to getting covered in the master degree module. So, just to describe everything and just to do a brief recap of what you're doing now in this first part of the lecture, is that you will need to understand that this is also crucial for knowing which is the difference between if you do something on math inside with, actually, for example, with pen and paper, and if you do any kind of mathematical computation inside the computer. So you will need to know which is the difference between actually continuous numbers and actually discrete numbers. And the basis of that, after providing some intuition that you already had from the audio representation module, then is how to represent numbers in binary format, and vice versa. That is actually relevant to know which is actually one of the first sources of numerical errors. And then after coping with that, then you will talk about actually the float representation of a number. And so how floats are represented inside the machine, and also doubles are represented similarly, but given that in the graphics module and the physics module we're going to use most of the time the floating point arithmetics, then you're just going to show how sine, exponent, and mantissa are here represented. And just going to provide you an intuition that I also have more in-depth outcomes in the handout, and how actually this kind of discrete representation generates errors due to approximations. And we're also going to find a way to quantify this error by just having a measurement of the total error itself. So this distinction between mathematical model, real world, and the computational representation is actually very crucial and relevant for a lot of things done nowadays in computers. Why is that? Because if you're trying to model anything happening in the real world, then always you're going to provide a model which is actually not necessarily describing what is actually happening, but it's just providing you representation of what it might happen and what you are perceiving as it is happening. So one of the examples why the world could be actually described in different ways is that you have two set of equations in physics to model the motion. You have the Newtonian's equation of the motion, and then you also have the general relativity. So the general relativity explains how particles or element moves when their velocity is very near to the speed of light, while on the other hand you could use new classic physics and classic equations of motion when this velocity is very small compared to actually the speed of light. So that doesn't mean that one of the two models is actually not accurate. The other thing is that the first model, the one that was described at the very beginning, all describes things that happens every day in everyday life, and that is also good to describe the thing that you experience in everyday life, while the other one needs to be used when you need to tune up satellite communications, for example, and because actually the communication is actually traveling with a speed of light, which is actually the electromagnetic field sent by the signal itself. And so in this situation, then the equations of the motion of the Newtonian physics won't work anymore. So that is also a relevant description of why the mathematical model is never the accurate representation of the reality. It's just another simplification of it. Another thing is that, for example, if you want to model a cloth, then you have the different models, but all of these models, or even if you're trying to use the springs or something like that, they're not the accurate. What is really happening in the world is just an intuitive explanation that has some kind of physics intuition behind of it. So that's why actually when you're trying to cope with a problem, usually you observe a world and then you try to formulate which is actually a mathematical model. That approach is actually called modeling, and in here everything is always in a continuous representation. So even Newtonian physics and also general relativity theory, they're all in the mathematical world, and everything is modeled in R, so in the real number space, or even multidimensional real number space. So the thing that you see here, multiple dimensions, that is also given by n in the natural integers numbers. So usually the thing that you're going to have in a company is that you will already have a mathematical model that is already known, but the thing that then you will need to do is to how to compute this mathematical model inside a computer representation. That is also the case when you're going to read a paper on an approach, how it is done, but that is not going to provide you necessarily which is the best approach and how to code that. And so you have another problem, which is actually the numerical computing one. And so that is another step, really, that is also going to provide you a lot of sorts of problems, because actually you're not going to describe everything with all the possible relative real numbers, but you're going to describe the world that you have only with a subset over real numbers. Before actually I provide you an actually theoretical formulation for that, I'm just going to provide you an intuition that also comes from the audio module on the same audio class for the same module, just to provide an intuition. There is also a huge difference between analogic sound and digital sound, and one is that, for example, is how the sound is recorded. So in the old days, when you have to record the sound in a vinyl, then you had that the pressure that is actually in the air, because actually the sound is transmitted in via pressure, so you have that is going to be compressed and also relaxed, and that is how actually the sound wave propagates. And all this sound wave is then intercepted by a cone that is going to ride inside of a vinyl, and that is also to create some kind of grooves. And inside of these grooves actually is where all the sound is going to be recorded. And actually in there you have all the whole space to record. Everything is in the real space, so you actually have all the possible information of the groove itself. So, because actually the sound is going to be accurately represented in all its pressure, and so you don't have any and so the thing that you're going to have is no loss of information whatsoever. While on the other hand, you cannot record an infinite quality in digital format. So the only thing that you could do is just to sample the sound as much as possible, and therefore you're going to approximate the information that you have. So in here you have two examples. One example is just the CD audio quality, and the other one you have a DVD audio output quality. So the only difference that you have between the two is that the DVD has a greater amount of space where you could store more information, while, for example, on the other hand, you have the audio output that only provides a limited audio representation, and therefore you're able to represent the sound in a less accurate way. So the more of the space that you have, the more is the accuracy of representation. But the thing that I won't stress enough is that for some of the problems, for example, numerical approximation and round-off errors, no matter how precise you are, given that you don't have the whole information available, still you won't be able to represent everything accurately as much as possible. And still, if the algorithm is not numerically robust, so numerical robustness is the way that I'm detecting an algorithm as being accurate. So if the algorithm is not robust, it's going to be not robust no matter how much precision I'm going to provide. For example, I have a double arithmetics, but if my algorithm is not accurate, it's going not to be accurate also in double arithmetics. So, after describing that, then you have how to represent numbers, also in math, and that part will be also relevant, and how to represent numbers also inside a machine in floating point arithmetics, as you will see. So, the most relevant part is the base, which is actually describing us, which are the digits that are required to represent the number. So, for example, you are accustomed to the decimal representation of the numbers. In this case, it means that the base equals 10, and that all the digits that are going to be used are the ones from 0 to 9. And then this representation holds for real numbers that are non-zero, okay? It will be also relevant in the next set of slides. And then any number could be represented by the maximum exponent, which is actually the most relevant digit. And then you have a set of integers representing actually the number. And why do you have here the part which is actually infinite in here? The reason why is that this representation is very relaxed, and through this you could also represent decimal numbers and also periodic numbers, or actually numbers like pi with an infinite number of digits, if you know all the digits of pi, for example. So the thing that you could do is, for example, represent 10. Then if you want to represent 10 in the basis of 10, that will mean that the biggest exponent having a non-zero significant digit is actually 2. is actually 1. So the thing that you will have is 10 to the power of 1, and the digit will be 1. So we'll have I equals 0 and alpha of 0 will be 1. And so also beta of to the power of minus 0. So by doing that, then you will have that I to the power times 10 to the power of 1. And then all the remainder digits will be actually 0. So actually you could represent then with this intuition all the possible numbers. So the other relevant thing is that given any number in any base, you could also convert that into another base. So if you have 89 in a decimal basis, then the thing that you will need to do is to just divide everything by 2 and just keep the remainder up until the end. And the thing that you will have at the end of the road is that all the remainders that you see here are going to provide you the binary representation of your number. So when you're using, for example, an integer, which is actually not necessarily a float, then the computer is just representing your number in this way. And what does this mean? So in a decimal representation, you could also use the basis representation to convert that back into the basis we're more accustomed to, which is actually the decimal basis. So if you take the same formula, then you have the greatest exponent is 6 in here. So you have 2 to the power of 6 of 1. And given the representation that you have before, then you need to sum all the other numbers. So you have 2 to the power of 4, 2 to the power of 3, and 2 to the power of 0. And the sum of all these numbers will actually give you 89. Then there is also another thing which is relevant and directly follows from this consideration, is that any decimal number which is actually not a power of 2, so also including the negative powers of 2 itself, then in a binary format is potentially represented as a periodic number. And so that in this case, the binary representation for decimal number is going also to provide you a first source of approximation, and therefore the reason why is that a lot of elements is going to be truncated. So, no matter how you try to create a numerical robust algorithm, if you have some kind of numbers that are already truncated, then you will have a source of approximation. So, that is something that you cannot cope with unless you try to minimize the number of operations that are going to reduce actually the summing up of all the problems of errors during the mathematical computation. That is a concept that you will also see later on. And so from this also follows how you are going to represent finite numbers. So finite numbers are represented as such. You have a specific representation for the 0, and as you may also see in the comments in the handout, you have specific representation for plus infinity, minus infinity, and not a number, so when you have a numerical float error, when you do, for example, division by 0. So you have specific number representations. And the other thing that you're doing is that you're not going to represent all the possible numbers, but you're only going to represent all the numbers in a given basis that are within a given power interval. So you have a lambda, in this case is just the minimum value of a power that the number could be represented, and you also have omega, which is actually the greatest power that could be represented. So everything follows from before. This is the change, so you don't have up to infinity here also, but you're also going to truncate all the digits to a specific subset of the digit itself, which is actually t. So you have that p, this kind of p, is going to represent the power field in your number. Then all this other part is going to be represented as a mantissa, and specifically in the mantissa we're going just to represent the alphas, because actually the betas are clear from the context. In the case of floating point arithmetics, it's just a power of 2, a negative power of 2 more precisely. And then you have also another part in the sign in here. And that is also called in floating point arithmetics a normalized representation, because there is also something called non-normalized representation, and that is only provided because you want to also accurately represent some other numbers that are near to zero. Otherwise, this representation is not going to accurately describe some number near to zero. So you have another set of finite numbers, ideally, that are going to represent smaller and smaller numbers. But given this representation, you could also formally prove that it also follows and derives the definition of a machine epsilon. So the machine epsilon is actually the smallest interval between the two numbers that the machine is not able to represent. So actually, it means that all the numbers within that interval are not being represented. In here, the distance is normalized, so if you have very big numbers or you have very small numbers, the machine epsilon will be the same, because that is also taken into consideration, which is actually the size, as to say, of the number itself. And for the machine epsilon, you will also have some definitions of a round-off or of a truncation of a number itself. So either if you take in 2 epsilon or epsilon, you will have respectively the truncation or the round-off error of a number itself. And then you also have other problems in here. Other problems will be if you're trying to do operations inside a computer and then the number that you're going to describe is too big and doesn't fit the representation itself. So you will have specifically 2 errors, the underflow and the overflow. So the underflow is when actually the power is very small, and so you're not able to describe the number in finite arithmetics, and then the overflow is the opposite scenario, when the number is too big and that cannot be possibly represented. So as you may want to consider in here is that one very intuitive result is that if a field that you're trying to model inside your video game is very big, and therefore maybe the distances are so big that then the floating point arithmetic is not enough, you should also try to reconsider how you're representing your field. One possible way to cope with a problem is actually to split the space into subspaces where actually you could also use floating point arithmetics more accurately. But then the thing that you will see is that inside the company you will have a lot of problems, different problems, and that are also not forecasted here. So in here we cannot forecast all the possible problems, so the thing that we're going to provide you is just the theoretical formulation, so you have the tools to cope as best as you can with this scenario. So another irrelevant thing is actually bridging the floating point arithmetics to this kind of definition that feels like to be very abstracted and far off from reality. But you could also consider is that actually if you take 24 elements for the mantissa and you take only the powers between 126 and 127, then you will see that the thing that we're trying to describe is actually the floating point numbers. And specifically, the thing that you're going to describe is just numbers that are using 32 bits, using a binary representation, so using a basis of 2. And so all the things that they're trying to do in here is to just describe, give some space for the mantissa over element for the exponent, and so you will be able to represent a lot of exponents which are the exponent from omega minus lambda plus 1 number of exponents. Before continuing in this slide, I think that that is also very beneficial to have also an intuitive way to represent the number itself. So you have the fraction part, which is actually called mantissa in here, and then you have the exponent itself, which is actually the exponent that is going to be used, and then you have a sign. And why actually is going to be like that is also provided in this source code. So if you go to the source code and you go to the numerical error part, I provided some source code showing you actually how the numbers are printed and represented inside the machine. So if we comment all the remaining part and we try to print this one, you will see actually how a number is represented. So how does that work? So the thing that we're trying to use here to decompose the floating point into the mantissa, exponent, and sign is just to use a union. So what is a union? A union is a C-like data structure which is actually telling the compiler that either, in this case, a float or a struct defined as such is actually good. So I could represent my data either as a float or as a struct. And specifically in here, I'm going to use bit fields. So the thing that I'm going to tell the compiler in here, given that I am in the big little endian architecture, is that the first sign, so I will have, for example, the sign part, then I will have the exponent, and then I will have the mantissa using 23 bits. While on the other hand, if I have big endian, then representation is upside down. So that's why, because actually the endiness is just representing the bits from the most significant to the less significant in different ways. So this code is also a port from the GNU C library. So I also ported that for Windows after including a lot of stuff. So you will also need to add the Windows H, which is actually providing you the endiness definition. So in here, the other thing that you will see that is also discussed in the handouts is how you're able to determine if something is not a number. So you have a specific value for exponent and for the mantissa. You have if something is an infinity when the exponent is the maximum but the mantissa is 0, and actually 0 will be any number with mantissa 0 and exponent being 0. So specifically, if the finite numbers that are going to consider are going to have less exponents than the representation itself. So two exponents are just used to represent specific cases, as not a number is infinity and 0. But actually, how could we print this, and how we could represent the float as this structure? So the thing that the union is doing is to say the float could be also represented as a struct. Well, actually, unsigned int is used for practicality purposes in order to decompose each part of a float in different bits and then assign those bits in actually fields of a structure. And that is actually the process that is done in here. So that is only available in Linux, because actually in Windows is not able to cope with that representation. So Windows, you need to do something slightly different. But anyway, the thing that you will have at the end of the road is similar. So even though you're not able to use this initialization, you will have other macros. Well, anyway, the thing that I want also to show you now is how this print number is printed. So after providing the number, as actually the IEEE 754 float, so I'm just assigning the value to the float, and then automatically the union is going to also to provide me a representation using this struct implicitly. So the thing that we could try to do then is to print the number in all its parts. So now I could print the sign, the exponent, and the mantissa either as a number or also as a bit set. So bit set is also a C++, novel C++ data structure that is going to show the number as actually a bit filled, and the conversion that to a string is actually showing you a binary string. So it's just providing you the directly representation of a string itself in another format. And then the thing that you will also see is actually, given this decomposition in sine, exponent, and mantissa, how to reconstruct the actual number. So you have explanation for that with all the math in the handout if you're interested to that. But the thing that you're going to have in here is that you also have a result. So you have a result, and then you have the power under which you're dividing the mantissa, which is actually the highest power that could be represented. This is not for non-normalized numbers, which is fixed. While on the other hand, for the normalized number, the other thing that they are assuming is that the most significant digit is always 1. The reason also in here is always described for in-depth purposes in the material itself. And then you have the mantissa, which is actually calculated, so the all are very minor part. And then you have the power, which is actually multiplied by it. So you have a similar concept. You have the mantissa in here, and then you have the power that you need to divide. And then you will need also to multiply by the exponent, which is actually a power of 2. And everything now it is printed. So just to show you what you should be seeing also Windows if you run this code now. After waiting a while for building, I'm using Linux at the moment, just for practicality purposes. Anyway, the thing that you will see at the end of the road is actually the number that was provided. If that is a normalized number, the sign, the value, the numerical value of the exponent and of the mantissa, the binary representation of the number itself, and all the parts of it, which is actually the numerical exponent and actually the result, which is actually going to show you that actually how the number was printed is matching with the formula. So just showing the correctness of the process that I did. So I'm just printing the number and printing that as a numerical representation. So we're done with that. So we could also comment that out, because the next step is going to move alongside with the error plots. So the thing that you're also going to describe is that any possible kind of operations, like for example the sum, as a floating point counterpart, which is actually defined in here by this O plus sign. So for example, if you have x O plus y, then you will have that the number you will be actually the x plus y, but actually you will also have an error associated to the computation itself. So that's why you also have an epsilon part associated to it. So, as a next step, everything that I'm providing you here is also described in depth inside the comments, just to provide a better insight. But after doing some mathematical proofs, you could also see that, for example, the most stable mathematical operations are multiplications, and there is or even divisions, and that's why because actually if you do any kind of numerical operation, then the error that you commit, or actually u, is a number near to the epsilon machine. But also the epsilon also depends on the architecture. So the result that was provided before is the best one, which is actually the same one that you also have in Intel machine, because they're very precise. But in the old days they had also machines with a lot of errors in the numerical counterpart, so the epsilon was actually 1. So it was just precise under the integrated methods, but actually using floating points it was not precise at all. Well, on the other hand, the thing that you could also see theoretically is that any sum or subtraction is actually going to create a catastrophic cancellation. And so, what does that mean is that when you're summing two numbers that are very small, or actually even they are very big, but actually the resulting number is tending to zero, then the error that you're going to commit in for that operation is very big. So two examples that you may want to consider of a problem when you have numerical operations is that when the delta time is very small, and so the delta increment is very small also. So that is also a contradiction, because if you want to do a simulation which is accurate, you need to use a delta time which is very small, but on the other hand, you will cope on the long run with catastrophic cancellation. And the other situation is then actually when the speed will become very fast, so we'll be actually going to another step. So for example, when you're moving backwards from one position to the other. And you could also try to confirm this intuition by just taking the equation of a numerical integration and try to check which is the case when actually the numerical integration of the speed is going to tend to zero. So that is going to provide you also a good intuition, an idea where actually the Euler integration method is going to fail. As I said before, you also have better ways to express that, but they're going to be slow and others are very complicated, so more advanced techniques are not going to be covered by this module anyway. And just an intuition why, even though you're committing a constant error, still you have errors, is that given by this use case example. So one use case is trying to implement this kind of operations of a power. So I want to express x to the power of y, and for example, intuitive idea on how to represent that is also the intuition that you had from school, is to try to multiply x, y minus 1 time. So you have an iterative implementation of that, but as you will going to see from the next example, that is not a very good idea, because at the end of the road you're going to sum up a lot of errors. But the better idea is actually to minimize the number of operations, because you see here the number of operations is actually proportional to the size of y, while on the other hand you will have a more robust and mathematical operation if you reduce the number of operations to actually a constant. So not to a linear value depending on y, but actually to a constant value depending on y. For example, in here you will have that the x to the power of y could be always expressed as an exponent in the Napier representation, Napier E, to the power of the natural logarithm of x multiplied by y. So why is that? Because actually you could express any number as e elevated to the log of x, and then you have x to the power of y, and then given the properties of the logarithms, then you could move the y that is inside of here outside, and then you have only 3 operations, one multiplication, one logarithm, and one epsilon. So Napier E. And then the intuition why that is the correct implementation of that, if you have a logarithm and an e, is also going to be provided by this source code that I'm providing you just as a suggestion. Even though this is very elaborate and convoluted, the concept that they have for implementing the power set operation is actually exactly the same. Given that here the basis is the basis of 2, then just using the logarithm of 2 and actually the exponent of 2, but the concept is identical and the same. But the difference is that in here they're also trying to do all this kind of operation of exponentiation and also the logarithmic computation within the same function, and the way to do that is convoluted. So I'm providing you from in the slide the source code if you're interested in that. But the thing that I'm also trying to show in here is that a lot of operations that you may want to implement are very complicated to do. So the thing that I'm suggesting is that as far as you can, just use libraries instead of trying to code numerical operations from scratch. But anyway, you could, in the worst case scenario, you'll be still able to implement something like the power set if you have the exponentiation of a logarithm like in here. And in here, the thing that you could also try to describe is that I want also to check the correctness of approach in computing the value here. So there are a lot of formulations of the error if you want to check which is the error committed by the algorithm, the error committed by the numerical representation, but the coarse-grained representation of the error, the coarsest one as possible, is just using the total error, which is actually the relative error. Why it's called relative is similar to the concept of epsilon. So I'm doing just the difference between actually the number that is returned by the function as expected, while the number is actually the actual real value, and the value computed by the coded function using a finite representation of the number itself over actually f of n. That is going to describe me, which is actually the relative error that I'm committing while performing this computation. So the intuition that I'm going to describe here is that, for example, you all know which is the Fibonacci sequence. So the Fibonacci sequence is just a sequence defined by that the next number is the sequence is defined by the sum of the two previous numbers, where the two initial numbers in the sequence are 1 and 1. So the next number could be 2, then the next number again it will be 3, 5 and 8, and so on and so forth. Then instead of using an exponential algorithm, really, the thing that you could try to do is to derive a mathematical formula, and a mathematical formula to do that in constant time is actually using Binet's formula. And given some intuition that is provided in the same source code and in the handouts provided in the source code, is that you could also derive this formula where actually given the number of the position of the sequences, then you're going to derive actually the Fibonacci number directly. So please consider reading the Big O notation handouts if you want to know more on how to obtain this formula. So the way that now I'm going to show in the code itself how you're actually committing the error is that I'm going to implement this kind of exponentiation using the iterative implementation. And then you have the custom Binet formula error, which is actually using the function provided by the C++ library for the power function. And then I'm going to plot the total error. So the thing that you will have in the code, if you try to run it now, first I'm going to show the code. So the thing that you're going to have is you have two formulas, one for the Binet formula with the error, and the other one which is actually the Binet formula without the error. So what is the Binet formula without the error? Is just actually using phi, which is actually the golden ratio, value similar to the one of the golden ratio, and then I'm calling Fibonacci sequence, and then I'm rounding the number. That is whole what I'm doing. Then on the other end of the road, how I'm implemented the Binet formula error. So instead of using the library one, I used the iterative power function, and the iterative power is just checking if the power is less or equal to 0, because in here I'm just considering integer and positive integer values, and if the power is 0 or less than that, then the number is always 1. If it is 1, then it always returns the base. Otherwise, you need to iterate for some times over the base to multiply that and then return the number. That actually is the same implementation of the other one, but I'm just doing the floating point representation. So, if you now try to plot the relative error from the number of Fibonacci between 3 and 19, this is the thing that you will achieve. So as you will observe, you will have that for a lot of times So for I equals 31 up until I equals 31, then you will always have that you will have no error whatsoever. The thing that you will observe here is that in all these kind of cases, the thing that you will achieve is that when the machine actually is accurate, then is never going to provide an error which is actually lower than the epsilon itself. So when the machine is actually going to give you a relative error is actually to have an error which is greater than epsilon, and as you will see here, is going to accumulate and accumulate the more that you compute. So at the end of the road, the more you do operations, then this error is going to accumulate, and if you increase the number of iterations, and therefore at the end of the road you won't have a precise result. So that is also the intuition what is happening using Euler method. And so, going back to the slides, the only thing that you will need to do in here is just use an algorithm which is actually more accurate to compute this kind of problems. Then, as I said before, there are other techniques and ways to actually do numerical computations that are actually trying to cope with the errors themselves, and that are also going to be covered in the math degree. But another and trivial approach is, what if I'm not able to cope with a mathematical way to get rid of all this kind of error? So the other thing that you could do is really try to use interval arithmetics. So the thing that I'm saying here is that I will suggest you this approach only if you're not able to cope with an algorithm that is going to cope by itself with numerical problems. So if the algorithm is not robust, then you cannot make the algorithm robust. How is interval arithmetic working? So the idea of it comes from measure theory. So whenever, for example, you have a ruler and then you need to measure something, so I'm making an example with centimeters and millimeters, then you will have that the smallest error that you could commit is actually on the order of the millimeters. And that is also makes sense because, for example, let's try to measure a desk with a ruler having millimeters. Then you will actually measure either a value which is not necessarily on scale, and then the value that you will have is either greater or less than the value that you provided, really. So given that any number could be expressed by minus or plus the smallest value that the scale could represent, then the thing that you could also try to do is to use an interval to express which is actually the minimum value and the maximum value that could be represented within the scale. And so the thing that interval arithmetic is doing as much as possible is really trying to, instead of cope with the errors, bound them. So the thing that it's doing in here is just to represent the minimum and the maximum and try to cope that the actual value actually lies inside the interval. So this approach is meant to be used, for example, when you do to use tests, but not necessarily when you want to compute something accurate. So that's why one of the use case scenarios when you use interval arithmetics really is just to use them in order to do inconsistency detection. In order to do collision detection. And collision detection really what it needs to do is to check if something is colliding or not. So if you just need to do that test, then this algorithm is more than fine. So the good part of interval arithmetics also is that you could override all the mathematical operations in here and then giving you an intuition why this is given like that. So let's suppose that you want to sum a number, then you have the numbers represented by the maximum and the minimum. So ideally, the value that you want to represent as a sum is the sum of the two minimums and the sum of the two maximums, and similarly you could do with a minus. Then you have another problem with multiplication. The problem with multiplication is that, for example, you do not know necessarily which the minimum and the maximum value will be, because actually if you multiply two numbers that are between 0 and 1, then the multiplication of these two numbers will be less than the one of the two numbers initially given. Well, on the other hand, if you multiply numbers that are bigger than 1, then you will have numbers resulting from the multiplications that are greater than the initial operand. Therefore, in order to not cope with all the cases and to reduce all the by case definitions, you just do the minimum between all the possible computations of a multiplication and the maximum between all the possible combinations of the intervals. And also division could be defined similarly. You just do 1 over the number of d and c, and then you'd also need to swap them, because if d is the maximum, then 1 over d will become the minimum and vice versa. And then you will also need to consider that 0 shall not be inside the interval. Similarly to other approaches in standard mathematics, otherwise, if 0 is within the interval, then it will mean that you will have a potentially division by 0, even if I'm not sure. So I'm just saying that I'm dividing by 0. That is the intuition. And similarly, you could just rewrite the thing that was given in here, the multiplication with the power set. So instead of actually doing all the possible multiplications, you're just trying to do the maximum between, or the minimum between a squared and b squared. And actually, if the number is actually, the numbers are containing the 0 as an interval, then you should also consider 0 as the minimum possible element. So ideally, that is also the thing provided in the implementation that I provided, and that is actually this one. So in here, you just create the interval by just providing the constructor x and y, but if you don't have the minimum or the maximum value, then c will actually represent a value as such, so where the minimum and the maximum value is exactly that one. And then I override all the mathematical operations, and furthermore, I just provide also a printing utility, providing the print of interval associated with that. So, if you go back to the source code in here, just try to comment this. You also have one property that you have from interval arithmetic, is that you need also to consider how numbers are represented, and one use case is actually in here. Also, that is also the same approach that I was also trying to describe before for numerical robust algorithms. So one of the problems that is affecting interval arithmetics is that if you have the same number repeated actually multiple times, then you will have a better accuracy if you just try to consider the interval only once, as is this in here. So you could also see that this representation mathematically is essentially the same as this one. So the easiest way to check that actually this is the same as this one is just to expand this in one single fraction, and then you will see that the outcome of it will be exactly this one. Sorry. So in here, it's just providing you which is the intuition of the number. Let's try to run it. So I need to go back to numerical error in here. So as you see in here, that the thing that is done is that I provided two functions that could be coped also with numbers, so you have 3 and 1, and therefore given that I overridden all the operations, then you also have plus and minus, so, and division. So in here I'm using interval arithmetics, and in here I'm just using numbers. So given, as you will see, that if you use numbers, then the prime and second always return the same value, while on the other hand you will have that this second function is more accurate. So how could I say that this is more accurate? Well, I see that the interval here is very small while this interval is larger. So the thing that you will have ideally is that if you have a lot of operations over an interval which is actually approximated something like this, so the thing that I'm doing here is approximated 3 as an interval between 2 and 9 and 3 and dot 1, similar scenario that you could also have with numeric operations, really when you start to accumulate errors. And then the thing you have here is that the first one is actually enlarging and enlarging the error and propagating that because you have multiple instances of x, while in this only has one instance of x, so the error is propagated only once, as to say. And here you have the application on how the intervals are actually replicated. So even with internal arithmetics, you will need to take specific care on how to cope with these numbers. But the good part is that you could do a very easy sphere ABB collision detection. So the thing that you could observe is that how could I say that two elements are colliding? So if, for example, I have a sphere and the sphere is just described, for example, from the center of the sphere and the radius, then you will have this equation in the 3D space. So you have the x, the y, the z, then the p will be the coordinate in any point, and then that equation actually will return 0 if the element is on the border of the sphere itself. Then you will have a value which will be actually less than 0 if the value is actually inside of a sphere, while the value will be greater than 0 if the value of the point is actually outside of a sphere. So you could use the same approach in here and try to represent this in interval arithmetics. So you will have the cx, cy, and cz, so you have the coordinates of the numbers, and you also have r of radius, and then you will need also to provide p. So in this case, the p that you're providing, px, py, and pz, are going to be, as you may see here, 3 intervals, given that we are in interval arithmetics, where the px will be the minimum of the maximum values of x, py will be the minimum of the maximum values of the y, and the z will be the minimum of the maximum values of the z, so it will be the minimum maximum values in the coordinates of a bounding box in an ABB. And similarly, the thing that you will have, and you may also want to try that, if that minimum value of this sphere equation is greater than 0, then necessarily the point lies outside of the sphere and otherwise is actually intersecting that. So as a final example, I'm also providing you the code. So that is the code. I'm just providing you a sphere at the origin of the axis with radius 2, and a sphere actually having x, 0, 0, and 2, 2, 2 as coordinates. So I'm just representing as a sphere, as you may see here, as a vector, and where actually the vector is representing the coordinates of the center and the radius. And for this library, I'm just using the OpenGL mathematical library. It is also provided in the source code itself. Then there is also the equation representation. So given the center point, I'm just then re-invoking the equation itself. So the thing that is doing here is just express that point in internal arithmetics to check if the point is inside a sphere or not, or if I have 3 intervals like for AABBs, and I have the c of x, the c of y, the c of z, and the r, which is actually just representation of the sphere itself. And then I have x, y, and z, and then I'm providing you the equation. Then the the collision detection is implemented in the ABB actually. So the AABB has actually a minimum coordinate and the maximum coordinate of the AABB itself. That is also provided by the constructor. That is just associating the value to the field in the class. And then you have the sphere test, something like this. So then the sphere is going to take a sphere, and then you're going to compute the equation from the sphere. So you have a minimum of x, minimum of x. So you're computing the interval as I described before. And then you have all the tests, if it lies outside, or for it intersecting the boundary of it, or if it lies full inside. So in this scenario, you have all this kind of tests that you could use. So actually, if you run the code now, then you will see that this kind of elements actually lies full inside this sphere. Or actually, in this case, it means that it intersects. The sphere intersects the ABB. So that's it for today, and when you will be in the master degree, then we're also going to describe the Gottschalk algorithm from OBB and overlap tests.